All right. Okay. Okay, so we will continue on the frequency response. So last time we have done on the low frequency analysis. Okay, so today we'll begin with the high frequency analysis. Okay, so like I mentioned, only common emitter are covered. Okay, all right, so this is how it looks like. Okay, so this one I have explained in the previous class. Okay, so the one that you have done during the AC analysis for all common previously is at mid gap. Okay, at mid gap. Okay, so this is how the amplifier frequency response looks like. So where it has the mid gap value. So at this mid gap, the gain, so this is gain versus frequency. The gain is saturated at certain point before it reach the cutoff point. So this is the cutoff point. So how do we get the cutoff point? Is at this saturation region, at this saturation range, okay, it will drop by 3 dB. Okay, and it dropped by 3 dB, and it reached at this region. The left side is the cutoff frequency, cut off at low frequency. At the right side is cut off at the high frequency. Okay, as you can see, we have done on the low frequency at this time. So the frequency response looks like this. Okay, look like this. Okay, so we will look on the example. Okay, after this. Okay. All right. So during mid-gap frequency, all the capacitor that we have done, okay, all the capacitor that, for example, capacitor in AC analysis, we short circuit, okay, but for low and high frequency, we have to consider all the capacitor. And we find the frequency at that particular capacitor. Okay, for the low frequency, this one, okay, where we include the coupling capacitor, the capacitor that you can see in the circuit. Okay, for example, we have 3 coupling capacitor over here at the source, at collector, and at emitter. So we have to include all these 3 capacitor in our circuit. Okay, in our AC circuit. Okay, today we will look on the high frequency. So high frequency, we didn't include all these coupling capacitor, but we include capacitor then that we cannot see. It means the internal capacitor. Okay, internal capacitor in between junction. Okay, so we have 3 junctions. Therefore, we have 3 internal capacitance, as well as the wiring capacitance at the input and wiring capacitor at the output. Okay, so we have derived for the common emitter, okay, this one. Okay, so what do? Okay, we know that frequency is equal to the 1 over 2 pi RC. Okay, R is the total resistor that you see at that particular capacitor, and capacitor C is equal to the capacitor at that particular capacitor. Okay, so for example, you have this circuit and you have 3 capacitor, coupling capacitor. We call it as a coupling capacitor. So we include all this coupling capacitor in our AC analysis circuit. Okay, what happened to the DC supply? DC supply will be grounded. All right, so low frequency, so this is how it looks like. Okay, so we draw all the hybrid pi model where we have R pi, GMV pi, and then we have to include also the RE because we want to put the capacitor CE as well. Okay, so that's why at emitter we have RE and CE, and as we go on we have R1 parallel with R2 and FLS over here. Okay, so we will look the coupling capacitor referring to all these capacitor. Okay, 1, 2, and 3. So number 1, when we do the analysis for CS, for example, okay, frequency, low frequency at the source, what happened to the other capacitor, CE and CC? Will be? Yeah, you will be a short circuit, okay, will be short circuit. So all that will be short circuit, and only CS is remain in the circuit, okay. Then you will draw the equivalent circuit like this, because you want to find the R equivalent circuit, which is you see from this particular point, okay. So what can you see here? R1 parallel with R2, parallel with R pi, and then series with RS, okay. Do not wrongly doing this by parallel or distillery resistor, which is it is wrong, okay, wrong, okay. You must parallel these two first, and then you series with this one, okay. So the frequency will be the total resistance, okay, 1 over 2 pi times total resistance and CS. Okay, and then we look at the capacitor CC. So the rest capacitor will be shorted. So only resistor involved, these two, by seeing from here, is the series of RC and RL. Okay, RC here as in the Z out. Okay, so the R total is Z out plus RL. Okay, the equivalent. So the frequency will be equal to 1 over 2 pi R T total times capacitor at collector. And then for the common ammeter, so the rest will be shorted, the CS and the CC will be shorted, only remaining the CE. So we need to find the R equivalent over here. So when we have this kind of R equivalent, when there is a current source as well as the voltage source, okay, we need to do the inject voltage, okay. So inject voltage means that we find the Z test over here. Okay, and then R equivalent will be equal to the Z test parallel with RE. Okay, so how do we find Z test? Okay, I believe that all of you have already known this. So Z test is by inject the imaginary voltage. So when you inject imaginary voltage, okay, V test and I test, what happened to this source? It will be shorted. The only voltage supplied during the test circuit, I mean during imaginary circuit, is just the V test and I test. Okay, so that's why all this the voltage source is shorted. So when the voltage source is shorted, okay, so only RS is remaining here. So RS can be straight away parallel with R1 and R2. So that's why the circuit looks like this. So you have R1 parallel with R2 parallel with RS, and you inject the voltage. So that's it. You find the KVL to find V test, and then I test. Okay, so Z test is equal to this portion. So R equivalent, okay, R equivalent is equal to the Z test parallel with RE. So the whole thing over here will be parallel with RE. Okay, so FLE is equal to 1 over 2 pi R equivalent CE. Okay, so I ask you to do this example. Did you try this example? Have you tried? So basically yes, okay. So basically it is the same thing, okay, like same exactly the circuit like this, okay, where now you have all the values, okay, you have all the values, right? So the derivation also same, so I'm not going to do it again with you, okay, because all the derivation are same, because exactly the same the circuit voltage divider. So we just look at the answer. Okay, so for this EC equivalent circuit referring to the low frequency, okay, we put the GMV pi, R pi, GMV, R pi and GMV pi and RE, CE, everything, okay, it is the same, okay. So by referring to the source, okay, so we put all these will be short, okay, so CE short, CC also short. So when this short, okay, you might need to draw again the circuit. So the circuit will looks like this, okay, looks like this. Okay, all the CE short, CC also short, and then you find the R equivalent. Okay, R equivalent equal to the R1 parallel with R2 parallel with R5 plus RS. Okay, as you can see from here, it is equal to the R1 parallel with R2 parallel with R5. Okay, equal to the Z in. Okay, this one, 4411. Okay, so all these are correct. Okay, so plus RS over here. Okay, and then you will get 1 over 2 pi blah 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 something, and you get the value 7.35 hertz. Okay, for those who has tried, is this calculation correct? I also have tried, and these are correct. Okay. Okay, now is referring to the so this one, the frequency at CS. Okay, so this one frequency at CC. Okay, so at CC, in this case at CS, CE and CC short circuit. In here, CCS and CE short circuit. Okay, so you are seeing from here now. Okay, just now you are seeing from here the FLS. Now this is FLC. So only two resistors involved. So these two resistors in series, RC plus RL. So you get this equal to 2 hertz. Okay, I think this is correct answer. Okay. All right, and then we move on to the Z test at FLE. Okay, so this is the region. So FLE. So to find FLE, okay, so frequency at CE. So this time CS and CC short circuit. Okay, what you do? Okay, so from this one, okay, from this region, okay, you are seeing from here, so you need to apply V test. Okay, so you need to apply to inject okay, find Z test, and then R equivalent equal to the Z test parallel with RE. Okay, so how you do it is like this. Okay, the same thing here. Okay, so Z test equal to the R pi plus R1 parallel with R2 parallel with RS over beta plus 1. Okay, as you can see here, so we took the same value because it is the same circuit, same derivation. Okay, parallel with RE, so you get R equivalent. So this is the portion for Z test. And this is parallel with RE, so you get 22.96 ohm, and FLE is equal to 1 over 2 pi 22.96 ohm times 70 microfarad, and you get 99.02. Okay, as you can see, so you have three frequency. Okay, 1, 2, and 3. Okay, so you have 3 values of frequency. So usually during physical test or physical exam, so you will be provided with the board plot and you will be asked to draw the frequency response. Okay, so if you look at the model for the frequency response, it is look like this. So the one that I have drawn at the earlier class the other day. So it looks like this. So this is mid gap. Okay, so maybe in the question you'll be asked to analyze the AC circuit, okay, and then the low frequency. So actually the shape for the low frequency is look like this, okay. So from center and it will decrease. So all these three frequency that you got just now, it is actually at any point along this low frequency, okay. It could be this first frequency, second frequency, and third frequency, right? So that's why when the question asks you to draw the BOT plot, okay, so you have to include all these three frequencies. So you have three frequencies over here. Number one just now is F. So FLE is equal to the 99.02. Okay, and then this is the highest. The second highest is FLS 7.35. And FLC is 2 hertz. So you have 1, 2, and 3 frequency. So how it draw, okay, like I said, so take the highest frequency here, okay, so this is, imagine this is your your BOT plot, okay, so take the highest frequency over here, which is, now please listen carefully, 99.02, okay, so at your BOT plot, okay, so for example, 99, so this one they just equivalently take 100, so 100 over here. So since this is by decade drop, okay, so 99 when you drop by decade, which is 100 in this case, they take it equivalent to 100. So drop by 1 decade, you will get 10 decade. So these are the decade drop, okay, from 100 to 10. Okay, listen carefully. All right. So for the first frequency, to the second frequency, it will be dropped by negative 20 dB. Okay, so this is your very first point. Okay, from 100 decade to 10 decade, you make a line over here, and drop by minus 20 dB, you also make a line over here. So in this case, 20 dB, sorry. Oh, this is by octave. Wrong one. Is it octave? Sorry, 20 dB is here. Okay, here. 10, 20 dB here. Here. Okay, here. So, as you can see, the first one by 20 dB. Okay, so starting from 0, okay, from 0, because the plot usually start from 0, okay, and then 100 to 10 is 1 decade, and then drop by 20 dB. So this is your intersection line. This is 20 dB. Okay, I have to write it here. So negative 20. Okay, so the line of negative 20 is this one. You draw a line over here. Okay, draw a line over here, and you have 10 decade over 10 decade. So this is your intersection point. Okay, so this is your intersection point. Okay, so your line for this frequency, okay, your line of FLE frequency, okay, is this one, okay, from this 100 to this red color one, okay, but then you, oh, all right, so but then, so this is your line, so just take this as your line. Okay, where do you stop your line over here? As you can see, this is a straight line. Where do you stop your line is at the next frequency, 7.35. Where does your 7.35? For example, in this example, they take 7.5. So over here, so you have to extend further your line up to 7.35 or 7.5. So your first line here is from 100 hertz to 7.35. Okay, so that will be stopped over there. And then you have to do it, okay, again. Okay, for the second one, this one dropped by 40 dB. Okay, so your line now stop here at 7.35 over here. So what you need to do, 7.35 drop by 1 decade is 0.75. Okay, you have to draw the line for 0.75 over here. Okay, drop by minus 40 dB. Okay, so there will be a long here lah. Okay, so for example, this one started from 24. For example, if it minus with 40 dB, it about minus 64. So it will go down minus 64. Okay. All right, so this sketch is not finished. Okay, if you draw by using board plot, then you have to plan. Okay, then you have to plan your plot must be, okay, for example here, so you must start it with this one minus 20, 40, 60. Okay, you know that you're gonna have a long dB over here, so you would start from minus 20, minus 40, minus 60 to minus 80. Okay, and so on. Right, so that is how you draw the frequency response on board plot. Okay, so this is how it looks like. So you're gonna have one slope for the FLE, another slope for the FLC, and the rest of the slope is the remaining frequency FLC. Okay, so you're gonna have three slope. 1, 2, 3. So first slope drop by minus 20 dB. Second slope drop by minus 40 dB. Third slope drop by 60 dB. All right. So it is quite tedious, okay, to draw the plot. Okay. So in online, last time, like this is a mass question where the student has to draw the board plot. I'm not sure the coming test and final exam, I mean the coming test too, whether you have to draw will be provided. Maybe we print out, I'm not sure, okay? But it is difficult for you to draw. Maybe you don't have to draw, maybe you have to sketch. So by sketching it, so you know lah. So you need to know, okay, the how to, even though you just have to sketch without proper scaling, then you need to know the method how to sketch it. Right? So next one is the high frequency response. So like I said, so high frequency response is referring to the internal capacitance that you cannot see. So internal capacitance for this high frequency, it includes all the junction capacitance. Okay. For example, in here, this is your collector, this is the base, and this is emitter. All right, so for this case, okay, each of these terminal, okay, between junction to junction, it has internal capacitance. Okay, as you can see, from base to collector, it has capacitor CBC over here. Okay, from base to emitter, you have CBE. From collector to emitter, you have CCE. Okay, this one. All right, and then what happened to all these coupling capacitors? So coupling capacitor in this case, okay, so this is coupling. So coupling capacitor in this case will be shorted. Okay, will be shorted. Okay, and also we have to include another one capacitance, which is W wiring capacitance, CW in at the input part, okay, and CW out the wiring capacitance at the output part. Okay, so you have to put all the capacitors. So in this case, high frequency, you're gonna have 5 frequency. 1, 2, 3, 4, 5. Okay. All right. So how to solve this high frequency is by using, the total capacitance and everything by using Miller theorem. Okay. So what is Miller theorem? So Miller theorem is any PN junction can develop capacitance. Okay, like here. So between junction has capacitance. Okay. So in an amplifier, this capacitance become noticeable between the junction. Okay, all the junction. So this we call it as a Miller capacitance. Okay, for BJT between junction has capacitance. If you have MOSFET, the next topic of BJT is MOSFET. So you also have internal capacitance between junction. So it is called as a Miller capacitance. Okay, so it affects the input and output circuit. All right, so this is how it shows for the Miller capacitance. All right, so this is your amplifier model. Okay, amplifier model. So the one that you have done the AC analysis, okay, the AV value, if you still remember, during the mid gap, you find the voltage gain. Okay, so in this Miller theorem, you will be using the voltage gain, okay, the AV value. Okay, so the equivalent circuit is actually looks like this. So from here, so the total impedance of the Miller impedance is the feedback impedance over here. But this feedback impedance, okay, so this is the feedback impedance. So okay, so this one actually can be split into two. Okay, at the input of your amplifier model and at the output of your amplifier model. So this is how it looks like when it is converted. So this feedback impedance is no more feedback between input and output, but it will be splitted out into two, become Miller impedance at the input and Miller impedance at the output. Okay, so this is the Miller input capacitance. Okay, so in this case, we will be referring to the capacitance. So why they notated this by Z? So it is can be capacitance and resistance, but in this case, it is capacitance. So this capacitance, so for example, you will see later because you're not gonna have the capacitors just in vertical. Okay, in this case, you can have capacitance in horizontal. So that horizontal capacitor will be splitted out into two by using Miller theorem. Okay, so voltage across Z. Okay, voltage across Z, which is this one, voltage across Z. So for example, if you have here, okay, so for example, if you have here one plus minus VF, so this is feedback. So we put this as feedback, for example. Okay, so how do you find this VF? How you find this VF? How to get VF?
From the node at the left side and the node the right side.
Yes, correct. So VF is equal to the V in minus V out. All right. Okay. So how about your V out in this case? Okay. Your V out is equal to, since you already have your AV, therefore V out equal to AV V in. Agree?
Yes,
Agree?
ma'am.
Yes, okay. So in this case, all right, so you have your V out over here is, so VF is equal to the V in minus V out, okay. So if we take again this, so VF, okay, is equal to the V in. So V out, we take this portion, minus. So V out is AV V in. All right. Okay, so if we take out the V in, therefore V feedback is equal to the V in 1 minus AV. Okay, so that's why they got this here. Okay, okay, so they got we are up to here. Okay, we are up to here. Okay, so next stop is current through Z. Okay, so for example, you have okay, current over here. So where is current IF? For example, I make it this as IF. So this is current IF. Okay, IF. So IF is equal to the what? So you have VF already and you have ZF. Therefore, IF is equal to VF over ZF. Okay, VF over ZF. Okay. All right, so you have that one. So VF over ZF, okay, if you put all the value over here, so you will get, so VF, you have the portion here, which is V in 1 minus AV, okay, V in 1 minus AV. So you have this V in 1 minus AV over Z, okay, ZF, okay. So now we want to find this ZM in the Miller at input, the total impedance, Miller impedance at input and total Miller impedance at output. Therefore, total Miller impedance at input will be equal to the V in over IF. Okay, because of what? Because it is at the input, the voltage across at the input is V in. So the current here is IF because it is, so this impedance has been splitted out into two. Okay, therefore the current flowing here is also IF because initially this feedback, okay, feedback impedance. So IF here going down. So at output IF going out. Okay. All right, so you will get V in over IF, yeah, and IF is represent as this portion, okay? V in 1 minus AV over Z, so you will get this, and finally the equivalent, okay, the equivalent, I mean the simplification from here, you will get ZM in equal to Z over 1 minus AV. Okay, so the Miller capacitance at the input, okay, will be equal to the this one, okay, 1 minus AV CF. Okay, so this is referring to this feedback. Okay, you will see later. Okay, feedback capacitance. All right. Okay, we'll look at later. Okay, so at the output here, it is equal to the ZM out. So V out, voltage across ZM out is V out. So current is going up. Okay, because current in this direction, it is feedback. Therefore, V out over negative IF. So you get, you don't have summarize, you have to simplify this. And finally, you get ZM out equal to Z AV minus AV minus 1. Okay, you just have to memorize only these two. Okay, this one at the input. Okay, this one at the output. All right. Okay, so F is the feedback capacitance. Okay, so let's take a look on the example here. Okay, all right. Okay, so let's start here. You have this circuit. Okay, so you have to include all the internal capacitance. So you have 1 here, 2, 3, and do not to forget wiring. So this is not Miller. So wiring here is not Miller. So what is Miller just now? I will show you next. Okay. So you're gonna have 1, 2, 3, 4, 5 capacitance must be included in your AC analysis circuit at high frequency. Okay, what happened to this coupling will be shorted, shorted, and shorted. So when CE is shorted, therefore RE is no longer in the circuit. Okay, so you have here base, collector, and emitter. All right, so I want to copy this for a while. Sekejap, eh. All right. So I've copied here. Okay, so you have 5 capacitance and the coupling is shorted. Okay, only remain in your circuit is the internal capacitance. Okay, as well as the wiring. Okay, so let's do the high frequency equivalent circuit. So it's going to be a long, okay, high frequency equivalent circuit. So you have put everything here. So put your GMV pi. So you have your GMV pi. So I might have to draw at the center here. Yes. Is it center? Yes. Over here. Okay. Okay. So you have GMV pi and you also have your since. Okay, this is collector. So emitter now here go to ground because we have no longer RE over there. So it will be grounded. So this is your emitter. Okay, and then what else do you have? So at the base here, okay, you have your R pi. Okay, R pi. Okay, so this is your R pi. Okay, all right. So let's start draw your circuit. Okay, put all the resistor. Okay, for example, I want to put my resistor at the back. Okay, so I want to draw like this. Okay, so this is your a bit far from here. Okay, so this is your R pi. So this is your base. Okay, all right. So what are the resistor you have at the base to emitter? So the same thing here. So from base to emitter, you have what over there? You have R1 parallel with R2. Okay, R1 parallel with R2. And then you also have, so VCC here grounded. Okay, and then at the base, okay, you have RS and VS. Okay, so this is your RS and VS. All right, so let's put all the junction capacitance. Okay, as you can see, you have now we want to do at the front part, which is from base to emitter. So from base to emitter, you have what capacitance from base to emitter, student?
CBE.
Yep, CBE. Okay, so you have your CBE. Put it here. Okay, CBE. All right. What else you has capacitance at the base? Can you see?
CWI.
I, correct. Okay, so you have CWI, which is wiring, total capacitance wiring at the input. So from base to ground. Okay, from base to ground. So you have another one here, CWI. All right. So what else? Okay, so we have done this. Okay, from the base to ground. Is there anything else here? Nothing, right? Nothing, right?
Yeah.
Yes,
Yes.
Okay.
yes.
Yes, nothing. Okay. So now let's draw at the output. Okay, at the output from collector to emitter. Okay, so from collector to emitter, you have, of course, you have to put your resistor. So from collector to emitter, collector to ground, you have RC. Okay, you have RC. Okay, and then from collector also you have RL to ground. Okay, is there any resistor? No more. Okay, no more resistor, only left with the capacitor. So what are the capacitor at collector to emitter? So you have,
CCE.
yep, CCE. Okay, so you have CCE over here. Okay, and then what else? CW out.
EWE.
Yes, CW out over here. Okay, so I told you just now you gonna have how many capacitor? 1, 2, 3, 4, 5. You only have 4 here. What are the left capacitor that we didn't draw it yet?
CBE.
BE already.
CBC.
CBE already done over here.
CBC.
CBC, yes, CBC. As you can see, you have from base to collector here, CBC. So this is quite an odd capacitor because instead of in parallel, now it is in series. Okay. All right, so this odd capacitor, which is, if you want to total the resistor, it will be like all your total resistor will be in parallel. Am I right? Okay, but for capacitor, if these two in parallel, therefore you you can parallel it by total by total the capacitor in parallel. Okay, what happened to this odd capacitor? So this odd capacitor will be splitted out into two at the input and output, and this one we call it as a C Miller at input, C Miller at output. This is what I'm talking about the Miller stuff just now. Okay, so this one, the impedance in at the feedback or in series. Now we don't want this because we want all in parallel. Therefore, we split it out into two, become input and output. Okay, so the input one formula will be equal to this one, 1 minus AVCF, and the output equal to the CF AV minus 1 AV. Okay, so we have splitted out this into two, and you have to redraw again the circuit. Okay, let's draw it together. So you have our, okay, so this is RS, VS, and then you have R1 parallel with R2, and then you have R pi, okay, and then you have CW in, okay, you have CBE, okay. Now CBC, you have another one here, which is CM in, okay. And then you have nothing over here at the input. Okay, you have GMV pi over here, okay. And then you have RC. Oh my God, sorry. Okay, you have RC, and then you have RL, quite long over here, okay? So, and then you have here is CCE, and then you have here is CW out, okay? Okay, you have another one, CM out, has been splitted out at the output, so you write also here CM out. So quite long, okay? So CM out. So this is the whole equivalent circuit of your high frequency respond. Okay, so this it is. Okay, so it's quite long that you have to do it. So usually, sometimes student in the paper they do it in landscape. Okay, but it's okay. Vertical also no problem. Okay, so now we want to find the total impedance. Okay, so as you can see, okay, similar to low frequency, okay, the effect of capacitor will be studied separately. Okay, and of course we have at the input part and the output part. Okay, the effective low frequency is obtained by the lower of the two frequency. All right, so it is here. So you have here R total, the R, because you know frequency is equal to the 1 over 2 pi RC. Therefore, you need to find R, total R, and the R total, we call it as a RTH. And also the capacitance here is at input. So you have RTH in, RTH out, and C in and C out. Therefore, here, I don't know why the book used TH instead of just R total. So just put RTH. So RTH at the input over here. And you have capacitance C in, C at the output. So what will be the RTH, student? So when VS is short circuit, so RTH in is equal to what? R pi parallel with R1, parallel with R2, parallel with RS. Okay. How about the C in, total C in over here? Also same, CW in parallel with CBE, parallel with CMI. Okay. So not finished yet. So you have at the, when you have at the output, you also have at the, when you have at the input, so you also have at the output. So this is RTH out and this is C out. Right, so that's how you get the everything there. Okay, so now let us derive what is the equation. Okay. Okay, so at the input, okay, input part and output part. Okay, so let's take a look on the RTH in. So what is our total at the input? All resistor in parallel. Okay, so you have R pi parallel with R1, parallel with R2, parallel with RS. Okay, so C in, what is C in? Parallel as well, right?
Yeah.
Yeah, okay. CWI, okay, parallel with CBE, parallel with CMI. Okay, so when you have total capacitance in parallel, therefore, what happened to all these capacitance? Therefore, C in is equal to parallel capacitance, total parallel capacitance. When you have in series, you have to 1 over something, something. So when this is in parallel, therefore?
Plus we must sum of the
Yes,
three
yes.
capacitor.
Yes, correct. I mean, so you have CW in plus CBE plus CMI. Okay, so you have this total are total resistor at input, total capacitance at input. Okay, so not finished yet. So this is at the output. So how about at the output? Okay, at the output, what are the total resistance at the output, students? Where you are seeing from here. So what are the total you are seeing from here? Okay, you are seeing to the left. Therefore, the total resistance only RC
RL.
parallel with RL. Correct.
Yeah.
Okay. Okay, RC parallel with RL. Okay. While C out is equal to all this in parallel. CCE parallel with CW out, parallel with CM out. Okay, forgot. Too many, right? CCE, okay, plus CW out plus CM out. Okay, done. Okay, done at the input and output part. Okay, done. Okay, now not yet done. Okay, what is CM in? Okay, this one. And CM out. Okay, so CM in over here, if you look at the Miller just now, input CM in equal to 1 minus AV. AV, which AV? AV that you have calculated in the past during mid gap. So can you see the relation between it? So if they want you to do the high frequency analysis, mean you have a long story where you started from the mid gap. Okay, from the mid gap, you have to find the voltage gain and everything first. Then only you will be able to analyze the high frequency response because you need the value of voltage gain just now. Okay, so 1 minus AV CF. Okay, 1 minus AV CF. Okay, 1 minus AV. Now my question is, what is CF? What is CF in this case?
CBC.
Yes, correct. Where the CBC just now, the feedback capacitance. So this one we call it as a feedback capacitance instead of in parallel. Okay, instead on vertical, it is in horizontal. We don't want this horizontal. This one we call it as a feedback. Therefore, we split it out into two, become CM in and CM out. Okay, and then this has become the feedback capacitance. So therefore, this one, it is actually CF is equal to the CBC. Okay, so this is for the CMI. Okay, how about the CM out? Okay, CM out, it is equal to the CF AV minus 1 over AV. Okay, so CF in here, so AV minus 1 over AV. CF over here is CBC, the same thing. Okay, so that's how you do it. Okay, so I think you have everything here. You can solve the circuit now if you are asked to find it. Okay, so that's it. Any question? For the high frequency, I think it may look long, but then I think high frequency is easier than low frequency. Okay, to me, okay, because you don't have to do the Z test whatnot. You just have to just parallel, just like that. Okay, the only thing that might be not confused, I think you already understand here. So if you don't understand what is feedback whatnot just now, so maybe you just have to stuck on your mind. Maybe horizontal capacitor is not allowed in the high frequency equivalent circuit. So this horizontal capacitor must be split into vertical by using Miller theorem. So instead of CBC, when you split it out into two, it will become CMI, C Miller input and C Miller output. All right, dear student, do you have any question? Hello? Hello?
Yes, doctor.
Yes, doctor.
All right, okay.
Doctor,
Okay, great.
I don't understand why the capacitance can be split into two.
So that is on the theory, okay, on the theory. So this is if this is transistor, okay, sorry, this is amplifier, okay. So all the circuit that you have done here, so this is the amplifier, BJT amplifier circuit, okay. So the junction, okay, the junction between base and capacitor, okay, base and capacitor, if you transform it into amplifier model, okay, so this is represent your amplifier, okay, your amplifier. You only have input and output. Because amplifier, you just want to amplify your signal, okay. If you have microphone, you have amplifier signal. But this now is disrupt, okay, we just want a one-way amplifier model like this, okay? We don't want a feedback, okay? So this one has become a feedback. So it is look like this, okay? We don't want this. We just want a one-way amplifier model where it has the gain at the center and also it has the input part and output part. However, whatever that in between it has become the feedback. Okay, we don't want this feedback. Okay, how we simplify this feedback? Okay, by using Miller theorem. So if you want to know more about the Miller theorem, so Miller theorem is where I simplify just now. So from the Miller theorem, it is basically where you simplify the input and output part. Okay, so from the Miller theorem, the impedance that connect the output and input terminals. So this impedance, okay, can be represented as the input and output like this one. Okay, so that's why you cannot find the total if you have this feedback. Okay, we want to simplify the circuit. Okay, we want to simplify this feedback. Okay, so we split out into two. Okay, by using Miller theorem. So now it become an input and output. Now your circuit has become more simplified, where you can total all the capacitor at the input and total all the capacitor at the output. Here you cannot do. So it is quite complicated to solve this circuit. Okay, so that's why we simplify at the input and at the output. All right. Hello.
Okay.
All right. Okay, so I think, okay, for a good exercise, I want everyone to try this example. So I give you about 10 minutes from now. Okay, so as you can see the circuit here, you have CW out. Okay, you have CW in, okay, and also you have CBC. Okay, can you find, oh, this is the long way because you need to find AV. No, it's okay. So I give you exercise, okay, I give you exercise. So you have to do this for the mid gap, okay, and then how about, all right. So I think, yeah, see, you have to find the voltage gain and everything. Okay, and then you have to find similar in, similar out. All right, this one. Okay, how about I take this as a take-home quiz? Do you agree? As your quiz too? So you have to submit this take-home quiz by Friday. Sorry, by Friday. I will set the time. Okay, so so this is quite easy and free for you because this is the take home quiz, so you can do it during your free time, okay, on your own. Okay, do not copy, because when I mark your quiz, I definitely can see who copy or not. Okay, so maybe you can do on your own, and I will open the submission on e-learning. So most probably the submission on Friday. Okay, is that okay? So what you need to do, you need to find from the mid gap, the voltage gain, AV, and then you do the analysis for the high frequency. So high frequency, what is all about? This thing about. Okay, this all thing about. Okay, all right. Are you clear with that? Hello?
Yes, betul.
All right.
Yes, clear.
Okay. All right. Okay. So it is quite long, right? Until Friday. Okay, you can do it tonight or tomorrow. Okay, during your free time. Okay, so if you have no question, I want to take 5, okay, before we proceed to tutorial. Student, I cancel that one as I forgot. Already have answer. So yeah. I think I want to do a take-home quiz lah. So I will find another question for the high frequency. I mean something like that too maybe. So but that one already got the answer over there. So you can do on your own and compare with the answer. Is that okay? But we will do quiz some other time and maybe a take-home quiz. All right? Is that okay?
Okey doktor, boleh.
All
Okay,
right.
okay.
Okay. All right. Okay. Okay. So please try that example just now. It is a good practice. Okay. So what I can see from reviewing your test paper, go on from one paper to another paper of student, what I can see from there? I can see student do exercise and student didn't do exercise. Okay. By just reading it, you think you can understand. Okay. But not writing it or do exercise. So that that doesn't work. Okay, doesn't work that way in circuit analysis. I think you have previous experience with the circuit analysis, especially in here electronic and device analysis. You have to do the exercise. Do the exercise means doing it. Okay, when I give you tutorial, you do the tutorial, you calculate the tutorial, you try to think of it and you draw the circuit. So that's why I can see definitely as a lecturer I can see okay this student do exercise, this student doesn't. Okay, so look so odd while you draw the circuit and everything. Okay, all right, enough with mumbling. Okay, all right. Okay, student, so let's discuss on the tutorial. Okay, I believe that all of you have, I don't know, did you try the tutorial? Do you try the tutorial?
Yeah, but just a few question doktor.
Just a few questions. Okay, I think I want to stop this recording.